This is another video where we're talking about something in pre-calculus that we've done in Algebra 2. And it's not so much that we're going to do anything new as we're expecting more from the student than we did in Algebra 2. So solving rational equations, there's really only one key idea, and we addressed it in should have addressed it in Algebra 2, which is that you cancel fractions in an equation using the least common denominator. Once you get that key idea, there's more to the problem, but it's not rational equations, because once you cancel the fractions, the equations generally become polynomial. I suppose if it's truly a rational equation, it will always become a polynomial equation. So we're going to talk about canceling the fractions. In case you missed it in Algebra 2 or need a refresher, I'm going to talk through my first example, the philosophy, a bit more than I would normally. And we'll see what I mean. For this first example here, the actual rational part of this equation is relatively simple, but what comes after might be a bit more challenging than you would have seen in Algebra 2. So this equation has only the one fraction in it, 4 over a minus 6. A over here by itself has a denominator, but it's only 1, and so it's hidden. We don't usually write it. And the same thing with the 0. So as I look through for my least common denominator, it's just a minus 6. 1 times a minus 6, if you like, but that's just a minus 6. So this is my least common denominator, and I'm going to cancel the fractions using it. When we don't have an equation, if it's just an expression like 3/4, or when you were adding two fractions together, you had to be careful about your fractions, and you had to do things like multiply the same thing on the top that you did on the bottom, or divide by the same number on top and bottom, which you have to do in order to not change the answer. But for an equation, we have the option of multiplying on both sides. So we're not going to multiply by a fraction. And when I say we're going to multiply by the least common denominator, I don't mean on the bottom as a denominator. I mean, we're going to take this denominator and multiply it to the numerator. So we're multiplying by a minus 6 over 1. And what this will do is actually cancel all of the fractions on our equation, as long as we've done it right. I don't recommend you write out the distributive property. Normally, it's just a lot of writing for not very much benefit. But if you find it helps you, I can't stop you. And I'm going to do it this time just to be very clear about what actually happens when we multiply. So because of the subtraction over here, we have to distribute. And every term gets multiplied by a minus 6. The important part of this is that the term with the fraction, the a minus 6, cancels. So the fraction is not a fraction anymore. It's just minus 4. And that's the whole point of canceling fractions using the least common denominator. The fallout, the side effect, is that everything else gets a little bit more complicated. Now, we'll see sometimes when we're doing this with fractions, only certain parts of the LCD cancel out in certain terms. But in this case, a is not a fraction at all. There's no canceling. We get a squared minus 6a. And we have minus 4 here. And of course, 0 times anything is just 0. What we have left here is a quadratic, which is fairly typical for canceling out fractions. But if you look, this is not going to factor nicely, because we would need two numbers that multiply to -4 that add to -6. So since we can't factor nicely, if you want to complete the square, you can, but the quadratic formula does that for you, and you probably have it memorized at this point. So opposite of b plus or minus the square root of b squared, which is 36, minus 4 times 1 times -4 makes positive 16. All over 2 times 1 is just 2. 36 and 16 is 52. To simplify the square root of 52, 52 is 2 times 26, which means it's 4 times 13. So the square root of 4 is 2. That leaves a 13 in the square root, which is good because those 2's will reduce. Now, if I'm going to reduce this, don't forget to divide both terms by the 2. So I end up with 3 plus or minus the square root of 13, which are the solutions to this equation. So as you can see, the canceling out the fractions, not too bad. But the solving what's left behind might be a bit more challenging in pre-calculus than it was in Algebra 2. You see a lot more quadratics and cubics rather than the linear equations when you're done. In my second example, you can see the denominators are more complicated, which is by design. B plus 3, B minus 6, that's two different denominators. I certainly have to multiply by both of those. Rather than multiplying by this quadratic without examining it, I'm going to factor it. If this were a real world problem, I would factor this with trepidation. But because this is a problem I got from a textbook, I'm guessing the factors for this are B plus 3 and B minus 6. But let's find out. I need two numbers that multiply to negative 18 that add to negative 3. So negative 6 and positive 3. Which come to me as no surprise, because those are the ones I have on the left. And as I said, this is a nice problem created by a textbook writer who wants to make students happy. Well, okay, maybe not happy. So looking through, our least common denominator must contain B plus 3. Our least common denominator must contain B minus 6. And our least common denominator must contain B minus 6 and B plus 3, which it already does. So I don't need to multiply by these again. Go through your list. Now, if one of these had a multiplicity of 2, if this was squared, I would need to square it in my denominator. It doesn't, so I'm good to go. You're not likely to see a level of complexity beyond this in pre-calculus, although as you move on through math, and also, I guess I can't speak for other professors and how much they enjoy torturing their students. So when I multiply this, you could write it out in distributed form. I'm not going to, because you should be able to keep in your brain one at a time. Just remember to multiply it through each time. And the most important thing to focus on is which of these factors cancels in which fraction. So when I multiply this common denominator times this fraction, the B plus 3s are the ones that cancel, leaving B minus 6 times 2B, which will be pretty easy when we come back to multiply that. When I multiply into my second fraction, the B minus 6 is what cancels, leaving B plus 3 times 3. I really wanted to just multiply that. Okay, and then when I multiply into the third fraction, both are going to cancel, leaving just 27. That's nice. So this is 2b squared minus 12b plus 3b plus 9 equals 27. I'll subtract that 27 over and combine like terms. So 2b squared minus 9b minus 18. Unfortunately, there's no common factor here. I got all excited when I saw the 9 and the 18, but 2 has a separate factor. So I'm going to look for two numbers that multiply to negative 16 that add to negative 9. That would be 12 and 30. Did I say 16? That should be 36. 2 times negative 18 is negative 36. I need two numbers that multiply to negative 36 that add to negative 9, and they are negative 12 and positive 3. So I'm going to split the middle up into those. Oh, I already had those. Wild. 2b cubed minus 12b plus 3b plus 9 equals, plus 18, minus 18 equals 0. I'll factor by grouping. So this is 2b times b minus 6, and this is 3 times b minus 6. So I've got b minus 6, and I have 2b plus 3 equals 0, which suggests b equals 6 or b equals negative 3 halves. At this point, we come into the other problem that you're more likely to see in pre-calculus than you did in Algebra 2, which is b equals 6. If we try to use it on our original equation, will force us to divide by 0 here. This is an extraneous solution because it's outside the domain of the original equation. It's not possible in the original equation, so it's not a good solution for us. B equals negative 3/2, however, is going to work totally fine. So watch out for extraneous solutions. With the methods we use for rational functions, the only source for extraneous solutions is going to be things that make denominators 0. That should be enough to get you started. Like I said, you may, when you're doing these, run into some of these that are cubic. So don't forget you can use synthetic division to factor out cubics or look for special paddings. But other than that, it should be everything that you've already learned how to do.